Welcome to the Nova Scotia Online Prospectors Education Program, a series of online presentations discussing the geology and economic minerals of Nova Scotia. This module is dedicated to Meguma Gold deposits. You got an introduction to Meguma Gold deposits in the Mineral Deposits of Nova Scotia module. These deposits are of most interest to prospectors in Nova Scotia, and so it makes sense for us to take a closer look. The purpose of this module is to discuss these deposits in more detail, looking closer at their distribution, characteristics, and method of formation, with the hope that this will assist in your prospecting efforts. After an introduction, we will discuss various aspects of Meguma Gold deposits, including their distribution, the geology of the rocks that host these deposits, the geological processes that led to their formation, alteration features that characterize these deposits, and this will be followed by a review. Nova Scotia has a rich history associated with gold, and like many other places around the world, no other material on Earth evokes the response from all segments of society that gold does. It is generally accepted that the first official discovery of gold was at Mooseland in 1860. Word of this discovery quickly led to the discovery of several other deposits, and by the end of the 1800s, over 50 districts throughout southern Nova Scotia had produced some amount of gold. There have been 3 unofficial gold rushes or periods of mining activity in Nova Scotia. The first was from 1861 to 1876, the second from 1882 to 1903, and the third between 1935 and 1943. The production level and gold exploration activity in Nova Scotia was affected by several factors. For example, many miners left Nova Scotia in the mid-1870s to seek their fortune in the Klondike. The 2 world wars correspond to low production, as seen in the graph, reflecting a lack of labor. In total, there was approximately 1.2 million ounces of gold recovered from Meguma Gold mines, not including the undocumented gold, which may have been substantial. Most people are unaware of gold mining's importance in shaping the history of Nova Scotia's rural communities. In fact, many towns we recognize today were founded on mining, and many abandoned towns were important in determining access routes still used today. These towns are well documented in a book by Mike Parker for anybody interested in learning more. This map shows the distribution of Meguma Gold deposits in southern Nova Scotia. In the module on the geology of Nova Scotia, we learned that southern Nova Scotia is distinct from northern Nova Scotia. Southern Nova Scotia is referred to as the Meguma Zone and is dominated by metamorphic rocks of the Meguma supergroup. The Meguma supergroup rocks host the Meguma Gold deposits, hence the name, and we will look closer at these rocks in a few slides. Gold deposits are found in discrete areas that have been referred to as gold districts. The inset map shows a portion of the eastern shore and the locations of a number of gold districts. The larger map shows part of the 15-mile stream gold district. The red lines represent quartz veins, most of which follow layering within the host rocks, and the pink areas represent historic tailings. In the following section, we will start looking at Meguma Gold deposits in more detail, starting with a review of the geology of the host rocks and the geological processes that created these deposits. As mentioned, metamorphic rocks of the Meguma supergroup host Meguma Gold deposits. The geological history of the Meguma Zone dates back hundreds of millions of years to when the original sedimentary rocks were deposited. Let's look back through time and see how these processes created Meguma Gold deposits. Geologists believe that the original sediments that form the thick sequence of metamorphosed sedimentary rocks of the Meguma supergroup were deposited in a deep ocean environment, similar to what we would see on the Atlantic Ocean side of Nova Scotia today. This is where the Meguma Gold story started hundreds of millions of years ago. The illustration shows the shallow continental shelf, the steeper slope, and the ocean floor. Sediments associated with underwater avalanches on the steep slope flowed down the slope and settled in fan-shaped deposits, highlighted in red, at the toe of the slope and onto the ocean floor. These underwater deposits consisted of layers of sand, silt, and clay. Over time, these sediments accumulated and were compacted. The orange and green colors on the map represent the Meguma supergroup rocks, which are comprised of a lower sequence that is sandstone-dominated, referred to as the Goldenville group, and an upper sequence that is slate-dominated, referred to as the Halifax group. This photo shows a typical sequence of Goldenville sediments, which is dominated by thick layers of metamorphosed sandstone with thin intervals of slate. The majority of gold deposits in the Meguma zone are hosted in the Goldenville rocks. This photo shows a typical sequence of Halifax group sediments from the former Ovens gold mine along the southern shore of Nova Scotia. These rocks mainly consist of slate with thin layers of siltstone and sandstone. Over time, the continents of Earth are constantly moving through a process known as plate tectonics. If we look at the map here, it is apparent that North America and South America and Europe and Africa were once together. About 400 million years ago, these continental masses collided, and the sediments forming the Meguma supergroup were compressed, heated, folded, and uplifted to create the Nova Scotia landmass and its metamorphic rocks we see today. This process was important in the formation of Meguma gold deposits. The results of continental collision and folding can easily be seen when we look at the geology map of the province. The patterns of green and orange on the map reflect folding of the sediments we've been discussing, with the Halifax Formation exposed in regional synclines and the Goldenville in anticlines. The photo illustrates what folding looks like at a local scale, with the arrow on the left pointing to a syncline and the arrow on the right pointing to an anticline. As we shall see, the fold structures developed in the Meguma supergroup rocks are important in the formation of Meguma gold deposits. So let's look at how these folds develop. The telephone book illustrates the mechanics of folding in a layered sequence of sediments, with the pages of a phone book representing rock layers. As the edges of the book are forced together, the pages fold and slip past each other, causing faults between the pages, and voids form in the hinges of the fold. These fold-related structures are excellent places for the formation of gold-bearing quartz veins. It is well known that Meguma gold deposits are found in the hinges of anticlines, those A-shaped folds defined a few slides back. The map shows the surface traces of anticlines across a portion of the Meguma supergroup rocks along Nova Scotia's eastern shore. Similar anticlines are found in the western part of the southern mainland. When we plot Meguma gold districts on the map, we can see the close proximity of gold districts with the anticlines. The association of deposits with anticlinal hinges suggests a strong relationship between folding and deposit formation. When we look at the gold-bearing veins at Meguma gold deposits, we find that veins occupy fold-related structures, that is, bedding parallel faults and voids in the fold hinges, like those we discussed earlier. This relationship also supports a link between deposit formation and folding. These deposits are known as saddle reef deposits, which is a well-known deposit type. This slide provides a generalized summary of typical Meguma gold deposit vein types. Many types of veins have been described in Meguma gold deposits. However, there are essentially three main vein types: stratabound or bedding parallel veins, cross-cutting or discordant veins, often referred to as fissure veins, and angular veins. Let's look at these various vein types in a bit of detail. Stratabound means veins are confined within a sedimentary layer, and these vein types are commonly referred to as bedding parallel veins. These veins occur within structures related to the slipping of one bed over another during the folding process, as described earlier. Three common stratabound vein types are saddle reefs, bedding parallel veins, and En-echelon veins. While all these vein types might appear different, they are all related and commonly occur together. Saddle reef veins form in the voids in fold hinges, and the name reflects the saddle shape they illustrate. Saddle reef veins vary considerably in thickness, as shown in the two photos. The photo on the left shows a relatively thin saddle at the Ovens Gold District, whereas the photo on the right was taken underground at the Dufferin Mine. Bedding parallel veins occur on fold limbs, occupying bedding parallel structures related to folding. They commonly have a laminated texture, and these veins are generally considered good for gold. The photo on the left was taken underground at the Mooseland Mine and shows a series of massive bedding parallel veins that contain gold. The width of the photo is about 1.5 meters. The photo on the right is of a typical laminated vein and was taken underground at the Dufferin Mine. This vein is associated with a saddle reef vein. En-echelon veins are common in Meguma Gold deposits and represent strata-bound veins as they are confined to slate layers. These veins reflect bedding parallel shear within the slate layer related to folding and sliding of layers over one another, but without the formation of distinct faults. Initially, they form as an array of horizontal veins, stage 1 in the figure, and progressively change orientation during folding, stage 2 and 3 in the figure. Crosscut veins occur in cracks that form perpendicular to the fold hinge and cut across bedding. These veins are sometimes called fissure veins, and several former gold mines are located on this type of vein. In these photos, we can see quartz veins cutting across bedding. The photo on the left shows displacement of a vein along layer boundaries. This offset reflects bedding parallel faults developed during folding, as discussed above. Angular veins are a distinct vein set that typically intersect bedding at an angle. Although not well documented, many historical records refer to the importance of angular veins to gold enrichment, with enrichment occurring where angular and stratabound veins intersect and/or overlap. These zones of overlap can define high-grade ore chutes within the overall vein system. These photos show the relationship of angular and bedding parallel laminated veins at the Mooseland Gold District. Both views are looking at the back, or ceiling, of a working. In the photo on the left, you can see the angular vein intersects and then follows the bedding parallel vein, and in this area of overlap, coarse gold was common. We have already discussed many of the common characteristics found at the majority of Meguma Gold deposits, such as geology, geological process, anticlinal folds, and the presence of quartz veins. Another characteristic common to Meguma Gold deposits is alteration. Alteration is a process that changes the host rock as a result of the interaction with fluids that form the veins. The most prevalent forms of alteration include arsenopyrite, carbonate minerals, oikocrys, and bleaching. Let's look at each of these in a bit more detail. In the photo, we can see well-defined arsenopyrite crystals disseminated throughout the lighter-colored siltstone layer. As we saw in the Minerals of Nova Scotia module, arsenopyrite is an iron arsenic sulfide, has a metallic luster, and is steel gray. It commonly forms prisms or diamonds, and striations of crystal faces are characteristic. Arsenopyrite can be found at all Meguma Gold districts and is a good prospecting tool. Carbonate alteration is common in many Meguma Gold deposits. Anchorite, an iron carbonate, and calcite occur in veins and disseminated throughout the wall rock. Disseminated carbonate is often difficult to identify in fresh rock and only becomes apparent on weathered surfaces where anchorite turns a brown color, as seen in the photos. The inset photo on the right shows weathered anchorite in a vein. Oikocrys is a term used for an aggregate of minerals. In Meguma Gold districts, the term oikocrys has been used for an aggregate of minerals generally forming elongated and cigar-shaped aggregates within slate and siltstone. In the photo, we can see well-defined oikocrys in slate. The larger crystals are approximately 1 centimeter long. Although there is no definitive explanation for the formation of oikocrys, they are restricted to gold districts and therefore appear to be related to the formation of gold deposits. In this regard, their presence can be a useful prospecting tool. Bleaching is a general term reflecting a lightening in color within the sandstone beds. The cause of this color change is not well documented, but it is generally thought to reflect an addition of quartz to the rock, referred to as silicification. To summarize, Meguma Gold deposits are found in metamorphosed sediments in southern mainland Nova Scotia. All Meguma Gold deposits are located in anticlinal folds, with quartz veins occurring in fold-related structures. All Meguma Gold deposits share a number of common characteristics, such as quartz veins, Carbonate Alteration, and Arsenopyrite Alteration. More information on Meguma Gold deposits is available in the Resources Links section or by contacting the Nova Scotia Department of Natural Resources.